Let's start today's class. So, in the previous class, we learned about the matrix multiplication in QDAR. So, actually, we learned about the software execution model of the GPU. So, the GPU processor exploit the thread level parallelism, and then also we learned that a GPU generates multiple threads from a single kernel. And then these threads are generated. GPU first group the multiple thread into the thread group, and then actually, so we also learned about the hardware architecture of the GPU, and then these thread groups are assigned to the stream process of the GPU. Okay, and then when these thread groups are assigned to the GPU, actually the multiple thread, thread group, also it is called a CTA, and then the thread in thread groups are packed into a warp, okay, and the warps are executed inside the one streaming multiprocessor. So this is the GPU's execution model, but actually this warp is not revealed to the software programmers. Okay, and then to the software programmers, GPU program model just revealed the thread group, so it's called a CTA, and threads are revealed to the software engineer, the software programmer. So actually, not to use the GPU, so we can use the OpenCL or QDAR framework to program the parallel kernel of the GPU. Then, so actually, we are learning about the NVIDIA GPU architecture. So, yeah, I will cover the QDAR programming model of the matrix multiplication. But this is not a programming course, so I will just explain the basic kernel. The basic kernel of the matrix multiplication. Okay, so because GPU used its unique execution models, and then we need to assign multiple threads to the execution of the repetitive computation. So actually, the matrix multiplication kernel is very simple. And then the matrix multiplication kernel requires the repeated add and multiply operations. So actually, also the matrix includes the large number of elements. So actually, this single element can be assigned to a single thread in the GPU. That's what we learned in the previous class. Actually, so as you can see, there are multiple elements in the matrix, and then this the result of the single element is assigned to a single thread in a GPU. And then think about that the GPUs are originally designed for image processing applications. And so we can also represent the multiple pixels of the image frame, the matrix, right? X, Y, the 2D matrix. Okay. And then actually for supporting image processing, GPU also provide the massive drive level parallelism. So which means that each pixel's values are assigned to the single thread of the GPU processor. Okay, and then so matrix multiplication is the same. The single element, the result of the single element is assigned to a single thread GPU. Okay, so we learned how to calculate the matrix multiplication. So actually, matrix multiplication is a very simple code. And also, but this matrix multiplication colors are widely used in our application, like neural network or scientific applications. Okay? So, and in order to perform the matrix multiplication, so it means that in order to generate the result of this element, then this column needs to read multiple elements. So actually, the elements in a single row of this matrix M, and also this not to calculate the result of this element, we also read the single column of the matrix, and this is the matrix multiplication M multiplied by M. So it means that for this single thread, needs to read the data from this data space for matrix M. So the data space of matrix M. So actually, what the orientation is different. So actually, for this computation, the entire row, the entire element in this single row to be read from the previous memory. Also, the element in the entire element in this column should be read from the GPU's global memory. Okay? But in order to execute the matrix multiplication, actually in order to execute this kernel and the GPU, then we need to organize the thread group and then the thread in a thread group. So actually, which means that as you can see, where is the kernel? Okay, so we need to define the size of the thread block. Also, we need to find the dimension of this thread block, which is a CTA. So actually, if we just calculate the matrix multiplication for large matrices, then this matrix, a single matrix, should be split into the multiple thread blocks. Then the multiple thread block also includes the multiple thread. So I said that each element is assigned to the single thread. So actually, we need to split this large matrix into the multiple thread blocks. So we need to consider this dimension under this matrix multiplication. But it is big. Why? But it is because of the GPU's hardware configuration, right? GPU is composed of multiple string multiprocessor, and then this multiprocessor can execute the kernel threads in a thread block. Okay, so this means that if GPU has the 16 SM, then also actually the SM can execute the multiple concurrent thread block. Okay, so this thread block should be assigned to the multiple SM. Then we can exploit the thread level parallelism GPU. If we just assign the only single thread block to the GPU hardware, so what will happen? If a kernel generates only a single thread block, a single CPA, then only one SM is used for computing the multiple thread in this single CPA. So even though GPU has a multiple SM, only one SM is utilized for parallel computation. This is the waste of hardware resources. So in order to exploit the thread-level terrorism, and we need to a single kernel need to generate the multiple thread blocks. So that's why this single matrix is split into multiple thread blocks. Okay. So this is another example. And then this is very important. So when a matrix multiplication is calculated in a CPU, then we also need to compute the indexes of the element of this matrix, right? So and it's same to the GPU. So even though GPU, for the GPU, multiple elements are assigned the multiple thread, but in order to access the target data, this doesn't target element in the matrix M or target element in the matrix M. Then we need to calculate the indexes of these elements. But unlike the CPU, the CPU, okay, let's see the CPU code. Even though this is the 2D matrix, then what we can represent the indexes of this matrix M and matrix N is the 1D dimension, right? Because it's like the row multiplied by V plus column. So in order to access the target data element in the matrices M and matrix N, then we need to also calculate the indexes like this. But these indexes can be easily calculated from the indexes of the target element. Right? Very simple. But when we write the GPU code, so it's a little bit it's more complex than the CPU code. But in order to, we need to organize the multiple thread blocks or the multiple thread in a GPU kernel. So we need to represent the row and column with the block indexes and thread indexes. Okay, so it means that the first we need to specify the target thread block of this thread using the block indexes. So for example, this is the 00, and then this is the 01, 02, 03, this is the 1, 1. So using the block indexes like X and Y, then we can calculate the block indexes of this thread block. Okay, this is 1, 1. Also, we know the dimension of this thread block. So we can calculate this one, the location, the indexes of the first thread of this thread block, right? And then also there are many threads inside of the thread block. So it means that using the thread indexes inside of this thread block, we can also calculate the indexes of this target thread. Okay. So we can calculate the row and column of this target element like this equation. Block index dot y multiplied by block dimension dot y plus thread index dot y. Actually, it's simple, right? So so for the matrix multiplication, we can easily calculate the row and column of this target element. Okay. But if we see this equation, so which means that this is the matrix multiplication kernel, which will be executed on the GPU. So which means that we need to calculate the row and column with the block indexes and thread indexes. The block indexes and thread indexes are fixed parameter assigned to the each thread, right? This is the fixed parameter. Each thread has its own block indexes and thread indexes, right? And then is a constant number of each thread. And then, so when a thread is launched on a GPU, these thread indexes or block indexes are assigned to each thread, and then using this parameter, then GPU calculate the sum of the values. Okay, so not just the data element. So in this example, this kernel calculate the row and column number of this thread using the thread indexes and block indexes. So why did I explain this? So actually, this is a very regular data element. So it means that these indexes are regularly assigned to the neighbor thread inside of the single CTA. So if these so in this example, so we are handling the matrix multiplication, and then the row and column is variables are easily is calculated from the block indexes and thread indexes using the linear equation. So which means that this row and column of these neighbor threads are regularly allocated. So it means that when the data are accessed by this thread, then this thread will request some data element regularly assigned in this memory space. And then this is very critical for the performance of GPU. Also the memory access patterns are also very critical for the performance of other processors like CPU or accelerator, but also it is very critical for the performance of GPU. So, and then these row and columns are used for calculate the indexes of target matrix of target matrix M and N. Here you can find the row is here and then column is here. Okay, so and this element is calculated, and entire row and the entire column is read from the GPU's global memory. Okay, calculate like this. Okay, this is the kernel code, and then I also mentioned the different configuration of the GPU's thread block dimension. Sorry, thread block dimension, and then thread dimension, thread block. So actually, so if you read the GPU specification, you can find the maximum number of warp, concurrent warp, also maximum number of concurrent CTA, the thread block. So actually, but based on the composition of the dimension of the thread block and then dimension of the thread in the thread block, and this the size of the thread blocks are determined. Also, based on the size of the thread block, the maximum concurrent thread block or maximum concurrent number of warps are decided. So why do we use GPU? We use GPU in order to exploit thread level parallelism. So usually, if more concurrent threads are running inside of the GPU, then we can increase the performance. But I said usually, we expect that if more threads more threads are generated from a single kernel, then we expect that, oh, we can increase the performance of this kernel. But it's not always true, because the GPU's performance is also determined by the memory traffic or some other factors. But the first step to increase the performance of a GPU is to increase the thread level parallelism. Okay, it means that the first step is to increase the number of concurrent threads which are executed on a GPU. Okay, so this is the first step that can improve the performance of a kernel which are assigned to the GPU. Okay, but as I explained, actually the performance of the GPU is determined by many factors. So actually the large concurrent thread is not directly related to the higher performance of the kernel. Okay, so that's why the NVIDIA provides the very detailed hardware profiler recently. And then also, actually, it's not easy. It's not easy to estimate the performance of the kernel on the GPU. So it is because the GPU runs the multiple concurrent thread from a single kernel. I said that the first step is to increase the number of concurrent threads in a GPU, but it's not always good for the performance. So when we want to tune the performance of our kernel, then we can also change the number of thread block dimensions or thread dimensions in the kernel. Okay, we can also check the performance of our kernel GPU. Okay, so now, I will explain the impact of the shared memory of the matrix multiplication kernel. So GPU has its unique memory system called the shared memory. And then this shared memory is not different, it's not same to the shared cache or shared memory of the CPU, right? So when we mention the shared memory system or shared cache of CPU, it means that this shared memory is shared by multiple threads. That is the meaning of the shared memory. But this data sharer is automatically managed by hardware in the CPU domain. When we mention the shared memory system or shared cache in a CPU domain. But the GPU, the shared memory different. It has the different meaning because the shared memory is actually scratch pad memory. So I already explained that scratch pad memory should be managed by programmers, not hardware. So it means that the programmer needs to fill the data in the shared memory space. Also, the programmer needs to use the data inside of this shared memory. Also, the execution of the multiple thread that access this shared memory should be also managed by programmers. Okay, that's why the GPU's shared memory is different from the shared cache or shared memory of the CPU domain. So because this is the scratch pad memory, then why do we use this scratch pad memory in the GPU domain? It is because the GPUs are originally designed for graphics application. So think like this. Oh, when multiple pixels in this single frame are processed by a GPU, we cannot compute the is large area is large area in the GPU kernel. So which means that because this frame size is very large, this frame can be also stored in the global memory. Then also a single thread inside of the kernel can request this multiple pixel data from the global memory. But what's the problem? If this entire pixel data are fetched from the global memory, and the global memory is slow, then it will take very long time. Okay, so which means when the image processors or multimedia processors are designed, then we just fetch the pixel data of the smaller area, and then these pixel data are stored in the internal memory of the processor. It is because we will use this pixel data very frequently, but if this pixel data is fetched from the global memory, whenever these pixel data are demanded, then it will take very long time. So it's like a cache, but the disadvantage of the cache is that the cache is managed by hardware. So which means that we cannot control the data move, data allocation, or data emission from the cache, because the data in the cache are automatically managed by hardware. But when our image processing applications are designed, we know that which pixels will be repeatedly demanded, and which pixels are repeatedly used, and which pixel is not used. Okay, so it means that actually when this pixel data of the large frame is processed, the processing engine takes only the pixel data of the smaller area, the internal memory. Then it performs the image processing algorithm for this pixel data in a smaller area. And then we fetch the different the next area in the internal memory, and then it just performs the processing. That is the idea of scratchpad memory. So GPU also has the shared memory, and because the CPU is, as I mentioned, the CPU is originally designed for image processing applications, and then which means that we can also exploit this scratchpad memory inside of the GPU for the faster application. Okay, so as I mentioned, this scratchpad memory is different from the cache. So we can also exploit the cache, which means that if we use the cache more efficiently, then we can also increase the performance, but it's not easy. So if the data access patterns are very regular and it's fixed, then we can exploit this scratchpad memory. Okay. Let's figure this access pattern from the global memory. So when we design a matrix multiplication kernel, so like this, so you can find that for the target thread, this target thread repeatedly demand the elements from the matrix M and matrix N. Actually, for the single thread, we just how many elements? K elements from the matrix M. Also, K elements from the matrix N. Okay. So, but think like the GPU's execution model. So GPU So actually this is the thread block, and there are multiple elements in this thread block. And then there are multiple threads. And then we already know that these multiple threads are packed into a warp. And then this warp is executed in the GPU hardware. So this thread, the single thread, demands the k elements from the matrix M, also another k elements from the matrix N. So which means that not calculate the result for this value, then is every thread, every single thread requires the 2k elements from the matrix M and matrix N. From where? Demand these elements of the global memory space. Okay. Actually, to the programmers, the programmer does not know about the cache. So actually, some data can be cached. Driving cache or add the cache of the GPU hardware. But to the programmer does not have any information about the cache. So it looks like that when these threads are executed, every element are fetched from the global memory space. So this means the GPU's device memory is DRAM. So what's the problem? So this thread, so this is single thread with the 2k. K is k the width. So which means that this is the width is equivalent to width. Then we also this k is changed from the 0 to width. But it's equivalent to 2 multiplied by width. Okay. The width is the width of the matrix. So when this thread requires the data from the global memory, then thread 1 also requires the 2 multiplied by width elements. Also, this thread 2 also requires the 2 multiplied by width elements of the global memory. Okay. And then it will take a long time. But we also find that we also can know that. So when this matrix multiplication is executed, and this is the neighbor thread, and then this thread are execute the matrix multiplication, the same thread it is the same row, also or different column. Okay. So you know the GPU also has the cache, but this cache can be used for exploiting the data locality. But the programmer does not know about the cache. So it means that even though the multiple pixels or multiple elements are repeatedly demanded by multiple threads, but programmer think that these multiple elements are repeatedly demanded from global memory. Okay, repeatedly fetched from the global memory. And that is the waste of that will degrade the performance of this kernel. So we can think like this. So if the small elements in the small area are repeatedly used by this multiple thread, then we can store these multiple elements in the internal memory, the internal scratchpad memory. Okay, so that is the shared memory idea. So if these elements are repeatedly accessed by multiple threads, then we can fetch the smaller number of elements inside of the on-chip memory, so it's the internal memory, and then the multiple thread can access this data from this on-chip memory. So, and also another benefit is that you can find that these elements are shared by multiple threads, right? It's a shared. But if this element is located in the global memory, then and these elements are accessed by thread 1, then it will take maybe 500 cycles. And then when these elements are also accessed by another thread, then it takes also 500 cycles, for example. But if this data is fetched from the on-chip memory, it's a very fast on-chip memory, like the Atom cache, then it will take only 10 cycles, or for example, maybe 5 cycles. Okay. So if we know or a certain data will be repeatedly demanded by multiple threads during some execution period, then we can fetch these elements to the on-chip memory, like the scratch pad memory, then this data, this scratch pad memory can be also shared by multiple threads. This is the shared memory idea of the GPU kernel. Okay, so which means that if we use the shared memory efficiently, we can effectively improve the performance of our this kernel. So, but what's the problem? The first, we need to fetch these elements in the global memory to this on-chip memory, and then until these data are entirely fetched to this on-chip memory, these multiple threads cannot start its execution, its computation. Right. So think like this. These elements are not fetched yet in the on-chip memory, but thread 1 or thread 2 can start the computation, because we cannot, if we cannot control the timing of the computation. And even though these data are not fetched to the on-chip memory, then thread 1 and thread 2 can start computation using this data. What's the problem? There will be wrong data, the incorrect data in this on-chip memory, and then these threads will generate the incorrect result. That's the problem. So, but we cannot estimate the data fetch latency from the global memory. Okay, and then these fetch latencies are influenced by many factors, like the data quality, also the location of the data, and then some many factors. So we don't know when these entire data are fetched to this scratch pad memory. And then we know that, but we know that this thread can start computation after all required data are fetched to this on-chip memory, the scratch pad memory. Then how can you solve this issue? We don't know when the data are fetched to the on-chip memory. We don't know if these are not synchronized. But we need to start after all required data are fetched to this internal memory, scratch pad memory. We need synchronization. Okay. So synchronization. So actually, the synchronization is the very critical idea for the parallel processing. Right. The CPU, so if you run some thread, so if you run the parallel multi-core programming CPU, then you need to understand the synchronization between multiple threads. Okay, because as I mentioned, we don't know when the required data are fed on this internal memory, because these batch requests are processed in the GPU hardware in parallel. Then also the latencies are influenced by many factors. So we don't know. But the multiple thread that read the data in the internal memory, like the scratch pad memory, need to start after the data fetch completes to the data fetch to the shared memory completes in the GPU. So the start of this computation will be synchronized. So I also mentioned that when I explain about the shared memory, then we need to control the start of the start time of the thread computation. So the start of this thread computation should be synchronized. So in order to support this operation, okay, the GPU will CUDA provide the API for synchronization of multiple thread inside of the single thread block or single CTL. This is called the sync thread. So sync thread supports the synchronization of this thread execution. So it's like the bar of the CPU domain, or it's the bar. So even though the execution times are different for the multiple thread inside of this CTA, so if there is a bar or synchronized API, the GPU kernel, then after this bar, the thread starts its instruction at the same time frame. Okay, so which means that the execution of instruction just after this bar or synchronization is synchronized. Okay, so even though these completion times are different, but the start time is synchronized after this bar. So in order to support this operation, the GPU also the CUDA, actually CUDA supports the sync thread API. Okay. So I will show some example here. So you can find that a sync thread here. Okay, so another sync thread here. So which means that this bar supports the synchronization between multiple threads. This is very critical for the parallel programming. Okay? Also, you need to remember that the shared memories are the data in shared memory is shared by thread inside of the same CTA or same thread block. Okay? So you can understand like this. So this is the thread block. And then we can assign some buffer space, like the internal memory or scratch pad memory called the shared memory, like this. So it's the shared memory. And then this shared memory is shared by the thread inside of the same thread block. So these threads share the same shared memory. And how about this? So, but I also mentioned that a single kernel generates multiple thread blocks. So which means, oh, there can be also another thread block, but this thread block also includes its own shared memory, but this thread can also access the same shared memory. But the thread in the different thread block cannot access this shared memory. It's not allowed. Okay, it's not allowed. So shared memory is it looks like the private memory inside of each thread block, and then this private memory is shared by multiple threads because the multiple threads are generated from a single thread block. Then this thread can share this shared memory of the inside of the thread block. So you can understand the shared memory like this. The private memory for each thread block. But this shared memory is shared by multiple threads inside of the same thread block. Okay. And how can we manage this shared block? So if you want to make use of shared memory on the GPU kernel, then you need to also design the data batch to the shared memory. So you need to design some data accesses to the shared memory for the multiple thread, the thread block, the same thread block. Okay. So let's think about the matrix multiplication kernel. So as I mentioned, this matrix multiplication kernel will generate the multiple thread blocks. Okay, and then this multiple thread is a single thread block includes the multiple threads. Okay, and then let's think about this. When this thread is computed inside of the GPU, then for this thread needs to be this entire element in this row. So when this thread, let us assume this is thread A and this is the thread B, then when this thread B is executed on the GPU, then this GPU, this thread B, needs to access the elements of this row. But if these threads are located in the same column and is the same column data. So in order to use the shared memory, but if this width is very large, then we cannot, even though this column is repeatedly demanded, the data in these columns are repeatedly demanded by this multiple thread, we cannot store this entire data of this column in the internal memory if the width is very large, right? So the size of the shared memory is very small compared to the global memory. So which means that we cannot store this entire data inside of the shared memory. Then what should we do? We need to split the matrix, the large matrix, into the small sub matrices. Okay. So this is the thread block. Okay, and then when we calculate the result of this thread, then we need to fetch the elements of this row and then elements of this column. But as I mentioned, if the width is very large, then we cannot store these entire elements to the shared memory. So which means that we need to split this large matrix into smaller sub matrices. So this idea is the same to the what I explained about the image processing algorithms. So because the frame size is very large, we cannot fetch the entire data to the internal memory of the processor. So we split this large frame into smaller data area, and then only these smaller data areas are pixel areas are fetched in the internal memory of the processor. It's the same as the shared memory. Okay, because the shared memory size is very small, we cannot fetch entire data of this row or this column, but we just fetch the smaller area. Okay, like this block, or and then this block into the shared memory, and then the next period, and we can also fetch the next block, and then also the next block into the shared memory. Okay. Also, so how can we fetch this data to the shared memory? We need to use the load instruction, right? So when we fetch the data from the global memory, then also we need to use the load instruction. But when this data is fetched to the shared memory, then we need to also use the different kind of load instruction. But this is also the load instruction. It's a kind of data fetch to the shared memory. Then how can we build this data into the shared memory? So GPU is the parallel processor. So, and then multiple threads are executed concurrently, right? So, which means when the data is fetched to the shared memory, each thread also execute its own load instruction to the corresponding location of this shared memory. So, for example, so this is the thread block, and then let us assume that this thread block includes the whole thread for this row, and then we need to build the data into the shared memory like this. So in this case, this thread, when this thread is executed, this thread fetch data element for only this part. Also, I need this part. Okay. This thread A, and then so this is the thread B, and then when this thread B also fetch this part and this part. Okay. So what does that mean? When we design the GPU kernel that makes use of a shared memory, then each thread also execute the data fetch for its own area. So we already know that when this thread is executed, then we need to read the entire data element in this row. But when the data is fetched, the data is fetched to the shared memory, then this fetch operation will be assigned to the multiple thread parallel. So by doing this, we can balance the execution of the multiple thread inside of the GPU. Okay, so this is also very important. So this is the kind of parallel processing idea. Because the data fetch or data movement also to be managed by multiple threads, we need to consider this parallel data fetch or parallel computation by multiple threads. Okay. So this is the some kind of example. So let us assume that we are is the thread block. So this thread block is computing matrix multiplication. So, and then this is the matrix M, and this is the matrix N. Then we need to perform the M multiplied by N. Okay. Then which data are required? So in order to execute this matrix, the multiplication for this element, then we need to require this row and this column. Okay. But as I mentioned, we cannot fetch the entire row data to the shared memory. So that means that this data, this element should be split. So this is the shared memory for the this thread block. So in order to calculate the multiplication for this one, then also this is the shared memory. This shared memory just includes the 4 elements. So first, we need to fetch this submatrix from the matrix M. So these elements are fetched to this shared memory. And for this, we know that in order to calculate this thread, we need to fetch this element and then this element from the matrices M and N. So this is the shared memory for matrix M. Then we need to fetch these elements into the shared memory. Okay. And then, then I mentioned that in order to calculate this one, then we need to collect these elements and then these elements. But only these elements are fetched to this shared memory here and here. Right? And then for this computation, for the computation of this thread, then we can read the data element from the shared memory. Okay. Okay, here, okay, here. And then also, in this thread block, there are multiple threads, and then so this in order to compute the matrix multiplication for the multiple thread, then we can also fetch the multiple data from this shared memory, right? And so we can use the data from the different threads. Then, in order to calculate the matrix multiplication for these elements, we also require these elements from the matrix M and matrix N. Okay. So after completing the matrix multiplication using this amount of data and this amount of data, then we need to fetch another submatrix like here and here. Do you understand? So after that, then we need to fetch these elements to the shared memory of this thread block, and then these elements this shared memory of this thread block. Okay. Then we can calculate the matrix multiplication using for this thread, then we can calculate the multiplication using this one and this one. Okay, and how the shared memory is exploited for matrix multiplication. Do you understand? So then we need assign the data in the shared memory. You can calculate the data location in the shared memory like this. So I said that the matrix, the large matrices are split into the smaller sub-matrices. So these matrices are called the tiles. Okay, so this is the width of this smaller sub-matrices is called the tile width. So we can calculate the indexes of the sub-matrix like this. Okay. And then, as I mentioned, because the data fetch latency is different, so the data fetch latencies are influenced by many factors, then we need to use the bar or barrier synchronization. So we need to use this ink thread inside our GPU kernel. Then let's see how the shared memories are assigned and how to use this shared memory. So as you can see, you can find this correlation. So inside of this kernel, the GPU kernel, then the shared memories are assigned. Shared memories are declared. So there are two shared memory space, yes underbar M. This is the tiled space for the shared memory, yes underbar M and yes underbar N. So as you can see, you can find the size of these arrays. This is the 2D array. These are 2D arrays, and then size of a single array is the tile width multiplied by tile width, which means that you just allocate the shared memory space for this kernel. Okay, so this is the shared memory space allocation. And which means that in the CPA, like the thread block, this amount of shared memory space is allocated. Okay, you can find the size of the shared memory is tile width multiplied by tile width. So you can find the block indexes or thread indexes like this. Then you can calculate the row and column of the matrix element using block indexes and thread indexes. Okay? Yes. Then how can we fetch the data into the shared memory? So you can find this loop. So if you see this loop, you can find that the P is less than N divided by tile width. Okay. So what does that mean? Because this thread block is computed for matrix multiplication. So we allocate the shared memory like this. So element like this. So in order to calculate this element, the result of this element, we need to fetch the entire data in this row. But we are using the shared memory, right? So we just fetch this amount of data to the shared memory. So in order to calculate the result of this one, then we need to fetch the multiple these tiles to the shared memory. Okay. So the width of this matrix is divided by tile width. Okay. And then is the fetch to the shared memory and then computation using the data inside of the shared memory are repeatedly executed inside of this loop, iterative loop. So you can find this data fetch statement. So it's a statement, but it's just the data fetch instruction to the shared memory. Okay, so you can, as you can see, so this is the thread index X and thread index Y. So that means that, oh, this is the shared memory space, and then thread index 0, 0 is allocated to the assigned the data element of this shared memory. Understand? So it's a thread index X, thread index Y. Also, this is thread index X and thread index Y. Then, when it fill is shared memory from the global memory space. So it's from the matrices M and N. So we use this shared memory for the matrix M, and then we use this shared memory for the matrix N. And we need to fetch the data to the shared memory, and then the indexes of the matrix M and N are calculated like this. Okay, so you can calculate these indexes like this. So, for example, and this shared memory is fetched. So this amount of data is fetched to the shared memory. Then we can also calculate the location, the indexes of this element using the thread index and then the time width of this shared memory. Okay, and then this amount of data is fetched to the shared memory, then we also calculate the location of this data. Then we calculate the indexes of this index of this data using the thread index and then the block indexes of this thread. Okay. So if you see that this one, then you can find that this is so not to fill this data, and also for the next iteration, then we need to fetch this element from the matrix M. So then we can calculate the location of this one and this. So row is row of the target thread, and then we need to. So actually, by the iteration number for fetching shared memory, then this is also we need to calculate this, and then we can for this matrix M, then this is located in the row of the matrix M. Then we can calculate the location, the indexes of this target data at this equation. Okay. Because when we fetch this one, the row and column on this one is the row plus this is row, and then column is the P multiplied by time width plus Tx, the thread index X. Okay, for the matrix M. And in order to fetch the element from the matrix N, then this matrix N is, and we can calculate the location of this column and also the column and row of this M. But if you see that this, when this data is fetched to the shared memory for this tile, then we need to also calculate the pixel location and the element location using this thread index and then block index of this thread. then firstly, the first iteration, we fetch this time, this amount of data from the matrix N. Also, and then for the next iteration, then we need to fetch this amount of data from the matrix N. So we can calculate the location of this element using the thread index and then the block indexing of this thread. Okay. So this becomes the row of the target element, and this is the column of the target element. So for each iteration, we can find that the shared memory is filled from the data element from global memory. So actually, each thread executes the data fetch operation that feeds the data into the shared memory. So as you can see, you can find the thread index here. Okay. Also, you can find. So this is the column. So column is determined by block index plus TX. Also, you can find the thread index here. So which means that each thread performs the data fetch for the data element, the single data element for its shared memory. So this is the parallel data fetch from the multiple thread. Understand? And we can find carrier synchronization. Right? As I mentioned, we don't know when this data fetch complete by multiple thread. So actually, this computation multiplication needs to start after the entire data is that's the shared memory. That's why we need to require carrier synchronization. Fast synchronization is our column. So which means that the execution of each thread is synchronized at this point. So when the data is fetched by multiple threads, then the latency can vary. So which means that the thread number 0, thread number 1, 2, 3, then we complete at this point, the data fetch complete at this point, and this point. So the fetch latencies are different, but we can find the synchronization API. But at this point, the executions are all synchronized inside of the CPA. Okay. So the shared memory is the private scratch pad memory inside of a single CPA. So this sync thread is the synchronization for multiple thread inside of the single CPA or single thread block. Okay. So thread executions are synchronized at this point, and using the fetched data, the shared memory, and we can calculate the matrix multiplication. Also, we can find another carrier synchronization. Why? Why do we require this? Why do we require another synchronization? So it is because this is thread number 1, 0, 1, 2, 3. So this is the data fetch to the shared memory. Let's just synchronize it. Then, as you can see, we need to perform stuff, multiplication and add repeatedly for different thread. The latency, the execution time can be also different. So like the multiply, add, multiply, add, also multiply, add, but this execution time can be different. But after this iteration complete, or one iteration complete, then also the data fetch will be performed by this kernel. So if this computation is not completed and the new data is fetched to the shared memory, then it will be computed using the wrong data. Okay? So it will generate the incorrect result. So that's why we require another synchronization, another barrier after the computation. So computation is synchronized. So computation is completed at this point, like a barrier, and then this data fetch is also executed for each thread. Okay? So we need to use this barrier and then this barrier for this matrix multiplication. Okay, so we need also another barrier synchronization. So benefit of the shared memory is that we can make use of internal memory, the best internal memory. Okay, and then, but not to use this shared memory, and we need to design our kernel using this shared memory declaration and the data fetch to the shared memory, also the barrier synchronization like this. So we need to design the kernel using some more effort. So which means that this kernel, this matrix kernel is more complex than the normal matrix kernel that only use the global memory space. But the problem is that if we just use only the global memory, then performance will be very low. So that's why we need to use the shared memory. But in order to use the shared memory efficiently and correctly, then we need to understand how the shared memory works inside of the GPU. Also, we need to design the multiple data fetch, the multiple parallel data fetch by the multiple thread like this. So we need to use the barrier synchronization. Then here and here, then we need to design the kernel with more effort. Okay. But the performance will be much higher than the normal matrix multiplication kernel. Think like this. So to the problem, actually we don't know the exact operation of the cache because the cache is parametrically managed by hardware. But if we use the scratch-pad memory or shared memory, then the data movement and then data inside of the shared memory are managed by programmers, which means that we can manage the data use or data movement in this GPU hardware. And then if this data movement, the data fetch or data use are efficiently managed by this kernel, then performance can be improved dramatically. Okay. So shared memory is different from the cache because the shared memory spaces are managed by programmer. And if we use the shared memory spaces efficiently, then we can improve the performance. But shared memory is also the limited resource the limited resource inside of a SM. So when I show the architecture of the streaming multiprocessor, then you can know that so each SM has the shared memory and level 1 data cache. Okay. The Fermi architecture, the size of the shared memory plus level 1 data cache is the 64 kilobyte. Now we can adjust the size of the shared memory or level 1 data cache inside of SF. Okay. So shared memory, the size of the shared memory is limited. And I explained that the shared memory is assigned to each thread block, each CTA. So then as you can see, when the kernel is launched, the size of the shared memory is also decided. So what does that mean? The limited hardware resource, as the size is determined when the kernel is launched. So the number of CTAs or number of thread blocks are also determined by the size of the shared memory. And we already learned that the size of CTA, the size of the concurrent thread are also determined by the thread block dimension, or also the number of the threads inside of a thread block. Also, because the shared memory is also the limited hardware resource, this shared memory size determines the number of concurrent thread blocks or number of concurrent CTAs. Okay. So let us assume that each SM has the 16 kilobyte of shared memory. Okay. Then if we use the time width as the 16, then each thread block use the 2 kilobyte of shared memory. Okay. Like the 16 multiplied 16 multiplied 4 by the required size for the single shared memory, but we require the 2 shared memory space for matrix M and the matrix N. So if we calculate this one, then it becomes the 2 kilobyte. So which means that each thread block requires the 2 kilobyte of shared memory. So in this case, if the SM has the 16 kilobyte of the shared memory, then this SM can run up to 8 thread blocks. Okay, if we just set the shared memory size as the 16, actually the tile width as the 16. Okay, but if we use the tile width as the 32, then the required size of the shared memory is the 8 kilobyte per thread block. What does that mean? In this case, because of the limitation of the shared memory size, each SM can run up to 2 thread blocks or 2 CTAs because of the shared memory. Okay. But we also learned that the number of concurrent CTAs are also determined by number of threads. Okay. So it is limited by also number of threads per CTA or the size of shared memory per CTA. So when we design the shared memory, then we also need to consider this extra configuration, this effect. Okay. So just remember that the number of concurrent CTAs can be also limited by shared memory size. Okay. Okay. And then another, so actually, so that's why the performance of the GPU is very complex. So another impact is another performance impact is the barrier synchronization. What does that mean? This is the synchronization bar, and then actually each thread has the different execution time. But if there are many synchronization barriers inside of the kernel, we cannot make use of rather than parallelism efficiently. So why? Because each thread has the different execution time. But let us assume this case. So this is the execution time of the thread, very short. But this thread takes very long time, okay, for data fetch. What does that mean? We observe that any other thread completes its operation at this point. But because of the barrier synchronization, then only one thread takes very long time. But because of the synchronization bar, only one thread are executed for this long time. Then GPUs cannot execute the other thread. So because of the synchronization, the TLPs are reduced. TLPs can be reduced. Okay? Which means that this amount of thread, the hardware resources can be wasted. But we don't know. We don't know the actual execution time of the multiple thread is very complex. So, but if when the thing is barrier synchronization are used, and TLPs can be also reduced, decreased. Okay? So that's another performance impact of the barrier synchronization. So it's very complex. That's why the parallel processing or parallel processors it's not easy to understand. So it's not easy to estimate the performance of the processing or parallel processors. So when the shared memories are used, we need to use the synchronization. But the synchronization is used, the TLP can be increased. So that's another performance impact of this shared memory model. Okay, so it takes a long time. So let's take a 10-minute break. I explain about the shared memory example of the matrix multiplication kernel. And then I hope everyone can understand this usage of the shared memory inside of the GPU kernel. Okay. Okay, let's take a 10-minute break. Then we'll restart the class at 12:13. Okay. Let's resume the class. So in this class, today's class, we learned about how to use shared memory in the matrix multiplication kernel. So, then now I will explain about the impact of the memory coalescing in the matrix multiplication kernel. So as I mentioned, the matrix multiplication is the very popular and the basic operations in the linear algebra. There's the other applications such as the neural networks. That's why we there's the matrix multiplication, of course. So this is a very good example of the parallel processing application. Then also, so let's investigate the impact of the memory coalescing matrix multiplication. So actually, we already learned about the memory coalescing. The GPU supports the memory coalescing now to reduce the number of memory transactions generated from the graph. Okay, and actually, then GPU also supports the very wide cache. So it is because if you need to support the high bandwidth from the device memory like DRAM, they not support the high bandwidth GPU explode the burst read or burst operation from the DRAM. And then actually the burst length of the GPU's DRAM is the 128 byte. The burst length of the CPU DRAM is the 64 byte, which means that actually usually the width of the one cache block of the CPU is the 64 byte, and the GPU's GDDR supports the longer burst length, so the more data in a single burst read. So GPUs supports the wider cache, which means that the length, the width of a single block, cache block is the 128 byte. And then what is the memory policy? So a single graph includes the multiple thread, and then I mentioned that these multiple threads generate the individual memory transactions. And then these transactions are merged into a single transaction. The data space of the requested by the requested address lie in the same cache line. Okay, so that is the memory policy. So people explain about the memory, the Coalescing impact of the matrix multiplication kernel. Let's consider about the DRAM. So this is the analogy of the memory bandwidth. So bandwidth is actually what's the bandwidth? So bandwidth is the amount of the data transactions between the processor and memory. So this is the memory. This is the memory bandwidth. Actually, we can represent the memory bandwidth using the amount of data, like the data size per second, like the certain megabyte per second. So this is the ideal bandwidth of the memory devices. We want very high bandwidth from the memory, but in reality, this is analogy. So actually, it's like the very narrow stroke from the data. So which means that compared to the required bandwidth from the multiple thread, actually in the GPU, the memory bandwidth is the very low, which means that the memory transaction or memory request can be the critical performance bottleneck in a GPU. So this is the organization of the DRAM. Actually, this is not an architecture course for the memory devices, but I briefly explain about the DRAM organization. So as you can see, this is the organization of the DRAM bank. The bank is the independent memory block. And then as you can see, the DRAM memory cell is the 2D array. Okay, 2D array. And then each bit data is stored in a single memory cell inside of this 2D memory cell. Okay, so it looks like this. This is the one line, and then this is the bin line, and then so this is the gate, then this is the capacitor, and then each bit is stored in this capacitor. So this is the organization of the memory cell of the DRAM. So now I mentioned that this memory cell is the 2D array. So firstly, based on the low low decoder activate this word line of the memory cell. And then if the word line is activated, then the bit data, the stored bit data can be read here, bit line of the memory cell. Okay. So firstly is word line activate the entire row like this one. So 2D array. And then this row is activated. Here this bit line, you can read the stored data from this memory cell. So the entire row data is read from the 2D array of this DRAM. You can find the sensor here. So this is the sense amplifier. It's an analog device. Then actually the entire raw data is stored in this sense amplifier. So sometimes the sense amplifier is called the raw buffer. Okay, it is because the entire raw data can be stored in the sense amplifier. And the DRAMs are also has the column address. So the entire row, multiple columns are included in this single row. And then based on this column address, then we can read, select a certain column data from this sense amplifier. Then we can read the data from the DRAM bank. That is the organization of the DRAM. So when the DRAM controller generates the DRAM command, then the controller sends the row address, column address. Also, DRAM chip has the multiple banks. So DRAM controller also sends the bank address to the DRAM. And we can read some data from the DRAM. But if we see the pin interface from the DRAM chip, and we can find that the data is just 8 bit per chip. So which means that at actually we are using the AA8 DDR, AA8 DRAM at DDR. Then also GDDR is the QDR, it's a point rate DRAM. So actually, every clock phase and clock edge, for every clock phase, we can read the byte data from the DRAM chip. Okay. But what's the problem? It's just 8 bit. It's very narrow, so it looks like that it's very narrow stroke DRAM channel. So if we just read out the 8 bit data from the DRAM, then it will be very inefficient. Okay, because the channel width is very narrow. So DRAM supports the burst operation, and then recently, we only use the burst read or burst write command to the DRAM, which means that even though the channel width is the 8 bit, it's a 1 byte. The DRAM supports the burst read or burst operation. So when the one command is given to a DRAM, then we can read 64 bytes from the DRAM. If the DRAM is the DDR, and then for the GPU, we can read out the 128 bytes. Okay, the one first read. So what does that mean? So DRAM data bit width is only 1 byte, 8 bit per chip. So in order to read the 128 byte, then and each phase and each T, and it just read the DRAM provides the 1 byte of data, 1 byte of data, then we can 1 byte consecutive data, then we can read out the very large data from the single DRAM chip, the 128 byte data. So this is the burst operation of the DRAM. And then as I mentioned, the size of the cache block or super cache block usually the same to the size of the a single burst read to the DRAM. Okay, so because this is more efficient. So if we just read out the 1 byte of data from the DRAM, then we need to generate the comment, the multiple comments for the another 1 byte, another 1 byte, another 1 byte, blah blah blah. But not because the DRAM supports the burst read or burst write, burst operation, and we can read out the larger data from the 1 rem command. Also, DRAM has some hierarchical structure, such as the multiple bank, multiple rank. And then actually the DRAM timing is changed by its organizations. So, but it's a little bit complex. So I will not explain about the details of the DRAM operation. But actually, this timing and the data in out are controlled by DRAM controller. Okay. So another performance issue is the DRAM refresh. So actually, the data should be refreshed in the DRAM. And then actually, this is another some performance factor of the DRAM. Okay. But so this is the first. So in order to support the higher bandwidth, the DRAM supports the burst operation. Also, DRAM has the multiple banks. So with the multiple banks, we can explore the memory level parallelism. Okay, it looks like this. So even though the interface is very narrow, but this interface is fast compared to the DRAM cells. Okay, but DRAM has the multiple banks. Bank is the independent DRAM block. So we can send the command to the multiple banks in parallel, and we can read out the data after some smaller delay for the multiple banks. So this is the memory level. This is called the memory level parallelism. Then in the multiple banks and then first read, we can increase the bandwidth to the DRAM channel. Then, so let's go back to the matrix multiplication kernel. The matrix multiplication kernel is executed. This kernel needs to access the large matrix. Then, I already explained that these matrices has the row-wise allocation. So actually, in the memory, then entire row is assigned to this memory, and then after that, the next row is allocated, and next row is allocated. Then let's see how these data are requested to. These data are fetched from the global memory, like the global DRAM. So if you see this kernel is a normal matrix multiplication kernel, you can find that this kernel requires data from the matrix M and then data from matrix N. And then we already know that this is the thread, the target thread. And in order to compute the result for this target thread, we need to read the data elements from this single row from the matrix M, and then data elements from this column from the matrix N. Then, so this is how the elements are requested. But we know that in a GPU execute the work, and then this work includes 32 thread. Okay, like this is the thread, and then actually thread number 0, 1, 2, 3 are assigned, work, and then we can represent the thread indexes as the 2D dimension or 3D dimensions, but we can. This is the matrix that we can represent the thread indexes as the 2D dimension, right? So like the x, y. So the threads are assigned to this work, then actually, firstly we allocate the thread index x first to this thread. So like that. So if the thread index of y is 0, then thread index of x is assigned to 0, 1, 2, 3, blah, blah, blah. So in a work, threads are allocated like this. Then, if we consider the coalescing, the memory coalescing inside of this work, and this row is requested by multiple threads, then actually is multiple threads request multiple rows. And then the work in the thread requests the data from the and then this request is the multiple data like this here and here. Oops. So until now, when we analyze the matrix multiplication kernel, we just consider the operation of each thread, each single thread. But we know that we are learning about the GPU architecture. So we know that when the GPU executes this thread, then threads are grouped into work, and the GPU executes the one work. Okay, and then this one work is executed, and then when the data is requested by thread in this work, and then when the one work is executed, then it just requests this amount of data and this amount of data. Then, if we just consider memory coalescing, we can know that when the data is accessed like this, so the data is accessed like this. So which means that the multiple data in the same row are requested in a single work. Which means, and then also I mentioned that this matrix data is allocated in the global memory, and we use the row-oriented location. So entire rows are allocated like this. So if the data elements are requested like this, then these requests are coalesced. Okay, so well coalesced well. But how about this axis? This axis, it's not coalesced. Okay, this axis is coalesced, but this axis is not coalesced. That is also another performance issues of this matrix multiplication kernel. So when the warp is executed, then the data in this matrix M. So we have matrix M by N. So when the data is read from the matrix N, then this data requests are well coalesced, but this data requests are not coalesced. What does that mean? When the warp is executed, and then this request will generate only one memory request, right? But when the request is, when the memory request is generated for matrix M, and this request will generate the 32 memory request. So because the memory request is not, requests are not coalesced, only one warp will generate the any request. It's not good for the performance. Okay. So if we just consider the coalescing this matrix multiplication kernel, so actually when the N is read, the data is read from the matrix N, those requests are well coalesced, but from M, it's not coalesced. So that's the problem. So it's like this. So it's not coalesced. Then, how can we solve this issue? So, if we just use the normal matrix multiplication kernel, then we cannot solve this issue because of the orientation of the computation. But if we use the shared memory, what will happen? So if we see the matrix multiplication kernel that exploit the shared memory, we can find that the kernel is executed, then first, then the thread in this GTA requests the data fetch from global memory space to the shared memory. And then we already know when we learned about the shared memory matrix multiplication, and this thread fetch the data from the global memory. This thread fetch this data from the matrix M, and then this data from the matrix N. And the next thread request the data from matrix N, and from this matrix N. So what's the benefit? So in order to fetch the data to the shared memory, then this is the warp. When a single warp performs data fetch to the shared memory, then this warp requests this amount of data and then this amount of data from the global memory. So what is the benefit? Actually, these requests are well coalesced. So this memory requests are well coalesced. So this is another performance benefit using shared memory. Okay? If we just design the matrix multiplication without shared memory, we call the orientation of this computation and then the warp formation. Then the data request for this matrix M are not coalesced. But when the data is fetched to this shared memory, the data requests are well coalesced. So this request then so this batch will generate the only one request from a single one. Then also this request will generate only one request from a single work. That is another benefit of using shared memory. Okay. So if we use the shared memory for the matrix multiplication, we don't need to consider about the memory corners. So we can need to modify the matrix multiplication corner in order to use the shared memory. But if we use the shared memory and then if we simplify the data fetch, the shared memory, then we can resolve the memory coalescing issue now work. Okay. So it's very interesting kernel design factor in a GPU. Okay. It is because because of the warp formation, the different design, the different kernel design also impacts the memory coalescing of this memory pair. Okay, so we can also redesign this kernel and make use of the shared memory. Okay, so even though I mentioned the previous section, previous topic, actually there are many factors that influence the performance of our kernel. So we can also make use of the shared memory. Also, we can make use of the various synchronization. Also, using the shared memory, we can solve the memory quality issue. There are many factors. So, which means that actually the CPU programming is a little easy. It's not, but because the CPU just only execute a single thread, and then actually the compilers can apply some compile optimization for the single thread. So GPUs are different. The GPU has its unique architecture feature, like work and thread blocks and shared memory. So there are many factors that decide the performance of the GPU. So which means that even though the kernel size is very small, then we need to consider these factors to improve the performance of our kernel. Okay. Okay, so I also mentioned the memory coalescing issue of the matrix multiplication kernel. So any question? Okay, so I will stop here and see you in the next class. 감사합니다.